Hi, I'm Donald Lee Johnson Jr. I teach at BatonRougeMagnetHighSchool, which is in East Baton Rouge Parish School System. As an educator, I am most passionate about motivating and inspiring my students to maximize their potential and motivating and inspiring my students to learn and to laugh. This lesson will cover solving systems of linear inequalities, and I'll be using the Springboard curriculum. It will be taught to a class of 9th graders. The students will be able to determine if an ordered pair is a solution to a system of linear inequalities, and also the students will be able to graph a system of linear inequalities to find out what the solution is. Prior to this lesson, we covered solving systems of linear equations, which set the stage for solving systems of linear inequalities. As a class, we also reviewed how to graph a linear equation in one variable as well as in two variables. My goal each year is to prepare each student for success on their or at their next level math class, and then also to give them the tools that they need so that they can perform at a high level on the LEAP 2025 test. Well, solving systems of linear inequalities is one of those things that they're going to need to know to perform well in their next level math class. And then also it's one of the tools that's needed so that they can maintain a high score on their LEAP 2025 test. So this class is about 50-50, meaning that half of the students are in class and the other half are virtual. And I found that using the document camera is the best way to maintain a high level of instruction for those that are in class and those that are at home. So for the most part, I will cast my screen so that those in class can see it on the big board, and then also those at home can see it big on their screen on their computer at home. So by doing this, I found that I can effectively engage all learners. Yeah. What would make this a system? It has more than one inequality. Fantastic. When you plug this order pair into both of these inequalities, it has to make both of them true. Not just one, but both of them. Or let me use my good English, both of them. It has to make both of them true. All right? Or should I say both of them? All right, so let's go ahead and take a few moments and see whether or not these order pairs are solutions to this system. All right, so -2, -3. All right, so for those of you at home, in the comments, I want you to type if it is a solution, yes or no. So -2, -3 on the count of 3. 1, 2, 3. Let's see what we got. All right, I see, okay. I see a no, I see a no. All right, no. All right, so class, what do you say in here? Say no? All right, hey, great job. Everybody saying no. All right, so yeah, definitely this would be a no. All right, and of course, we know the reason would be because, you don't get a true statement for both of them. All right, those of you at the crib, so is 3, -1 a solution? 1, 2, 3, go. Type it in. 3, -1. Oh, we kind of slow. Okay, let's see. We got a lot of no's. We got the no. We got the no. No. All right. On the count of 3. 1, 2, 3. No. All right. No. Okay, good. So again, in order to check to see if an order pair is a solution to a system of linear inequalities, when you plug that order pair in, it must make both inequalities true. If just one of them's true, it's not a solution. But if they're both true, it is a solution. All right? Any questions? Anybody need clarity? Good? Miss Rouse, what must we do with this inequality? Flip it. Hey, you use that correct English, loud and proud. Use the correct English, what must you do? What? I need Miss Ross and Ross to go to my school of correct English. We know the correct English would be flip that mug. Oh, I'm sorry. The mug needs to be flipped. Miss Ross and Ross like, no. Okay, my bad, Miss Ross and Ross. Yes, you have to reverse the inequality. You must reverse the inequality. All right, thank you, Miss Ross and Ross. Flip that mug. Okay. All right, so cool. So now you can see where the overlapping region was. Right here is the solution region. And this tells us that any ordered pair, all right, any ordered pair in this region will make both of these inequalities true. We can substitute any ordered pair here. It'll make both, because remember, in order for it to be a solution, it has to make both inequalities true. So Campbell, you've been doing a great job with this. Let me ask you this question, Campbell. The ordered pairs on this piece of the boundary, would these ordered pairs make both of these true? On this piece right here, this broken piece. On this broken part of the boundary, will it make both of these true? All right. Campbell, why is this broken? It's not equal to. Oh, so coming out of Campbell's mouth, she says, this is broken, so that means it's not equal to. So the question is, will these ordered pairs satisfy both inequalities? Good. No, because it's broken, so that means you don't include these. All right, so on this piece of the boundary, we know, hey, these ordered pairs will not be included. That's why it's broken. Okay. Campbell, what about the ordered pairs on this piece of the boundary? Would these ordered pairs be included? Okay, good. Yes, because that's why it's solid. Because remember, this said or equal to. This doesn't say or equal to. All right. So again, make sure both inequalities are solved for y. And then once you do that, go ahead and graph both of them on the same x and y axis. And I would suggest just shade a little piece. All right, just shade a little piece. And then you find out where the little pieces overlap and then darken that area. Okay, then darken that area. Okay? All right, so I'm going to give you a few moments and I want everybody to do part B. And of course, you can see, well, hey, you see where these two intersect. So you have this going this way, that going that way. So the solution would be all the ordered pairs in this region. And can y'all tell I used to teach talented art? Can y'all tell that? Yeah. Like, yeah, right, Mr. Johnson. Blah, blah, blah. All right, so the solution to this system of linear inequalities would be this region right here, this solution region. Now, would we include the ordered pairs on this piece of the boundary and on this piece of the boundary? All right, so let's see who we got. Angelina. All right, will we include the ordered pairs on this piece of the boundary? Yes or no? Yes. And how do you know that? All right. And what about this piece of the boundary? Yeah. All right. And the same situation. All right. Good job. So now check this out, guys. Check this out. They started by giving us the solution. You don't have the system of inequalities. So what I want you guys to do, I want you to write what system this would be. So Jolie, would you like to give us the inequality for L sub 1?
Y is greater than or equal to x plus 3.
X what?
X plus 3.
All right, so Jolie says y is greater than or equal to x plus 3. Let's examine that. So the most, straightforward thing we see, it crosses the y-intercept at 3. So we know it's going to have to end with plus 3. Uh-huh. All right. So then we say, okay, well, to get right here, so we're saying our slope is 1. So that means if we go up 1 to the right 1, we're back on the boundary. So if we go up 1 to the right 1, we're... Jolie, are we back on the boundary? So Jolie, make an adjustment. See, life is about adjustments. It's okay, we're going to make an adjustment, and we're going to get it right. We're going to get it. Okay, so Jolie, instead of this slope being 1, what that slope be? All right, so remember for slope, remember it's, let's see, so M is delta y over delta x. The change in the y over the change in the x. So to get from this point to this point, how much do we go up? 1. So that's going to be 1. And then we go to the right, how many? 2. Jolie, what that slope is? It sure is, girl. It sure is. Play with her. All right, good job. Y is equal to 1/2 x plus 3. You did your thing, Jolie. Hey, okay, yeah. So Crawford, what it do, dog? What it do? Crawford's like, it does nothing, but I'll answer the question. Okay, all right, Crawford, what you say, guy?
Y is less than or equal to negative 2x plus 3.
All right, so let's see what we got. Crawford, did your thing, boy. You made a do what it do. You know what I'm saying? You made a do what it do. Bam. Okay, so yeah. So as I think about today's lesson, I do believe that the objectives were met in part. For the first objective, when checking for student understanding, whether in class or virtual, the feedback was strong as it relates to student understanding, which gave me the impression that the students understood what was being taught. For the second objective, we've got some work to do. It took a little longer than expected for the students to be able to grasp the solutions. When I walked the class and examined the students' work, I could tell that many of my students didn't have a full understanding of the material. Next time, I will do more review of graphing linear equations and linear inequalities because many of my students had difficulties doing that. By doing this, I believe the students who struggled would have confidence that they could do the work, which I believe would lead to a better understanding of the material. Next class, we will thoroughly go over the homework, and then after that, I will assign 2 more problems and then check for understanding. Hopefully things will go well.